and maybe what we can do finally is to also look at an example of the same thing with a T flip-flop. Okay, so let us look at that example here, where I'm going to start with a T flip-flop based example. I'll again start with a circuit diagram. Okay. Yeah, okay. So in a T flip-flop, it's very important to remember that you also need a reset signal, because you remember in a T flip-flop, the characteristic table always deals with either you're going to you're either going to retain the state or you're going to complement the state. So unless you set the state of the flip-flop using some other control, you can never get into a known state. Okay, so therefore in a T flip-flop you always have to use a flip-flop that allows a reset to be asserted. So when the reset is high, you have to make sure that the output of the flop is a 0. Okay, so therefore here what you will do is, I will always put the clock below here. Okay, okay, this is my clock. Right, and I have a reset out here which is going to control the T flip flop. Okay, so this is the output. Okay, I'll call this Q and I'm going to call this reset. Okay, so I'm going to call reset. Okay, and based on this we are going to see how we can generate this state equation and state table and so on, right? So I have an input X, right, and the output B, okay, this is A, this is B, okay, and I have the reset here, and so what I'm doing is I also have an AND gate here. Okay, and this is my Y, right. So the point here is you are able to reset, and therefore you can assume that the system will always start with A and B in 0 0 state, right? You assert reset, make sure that it starts with 0 0, and then you allow it to go through. You take the reset off, and then the input can and the states can then decide what has to happen through the remaining cycle. Okay, so that is the only thing that you have to keep in mind here. So now again going back, what is combinational block 1, combinational block 2? Well, this is combinational block 1, right? And what about T, by the way? Oh, sorry, I forgot the second input. Yeah, okay, so okay, so this is combinational block 1, okay, and this is a very simple combinational block 2. conditional block 2. Okay, so again the number of flip-flops is 2, number of inputs is 1, number of outputs is 1 as per our convention, right? So based on this we can go ahead and write our state equations. So what are the state equations now? I am going to just simply write the TA of n plus 1, okay, the toggle input for the flip-flop whose output is A, which is flip-flop 1, and this is flip-flop 2. Okay, TA of n plus 1 is simply going to be B times X, Bn times X. Okay, TB of n plus 1 is equal to just X. Okay, and what the output Y is therefore going to be just AN into and BN. Okay, so these are my state equations, and based on this I can go ahead and generate my state table. Okay, state table, again I have 2 flip-flops and 1 input, and therefore I have to worry about 8 combinations. So I will basically take this guy to the next page. Yeah, okay. Now what is my T flip-flop characteristic table? It is T Qn plus 1. If T is 0, you just retain Qn. If it is 1, then you make it Qn bar. Okay, and of course you also have a reset, and here the idea is if the reset is 0, right? If reset is 0, then you don't do anything. Otherwise, if it is 1, then it doesn't matter what the T input is, the output will be a 0. So the point is you assert reset so that the flip-flop state comes to known output of 0, and then you proceed with the experiment. Okay, so now you go ahead and write the state table. Present state, input, next state. Right, and we are talking of TA and TB. Okay, flip-flop inputs. Actually, inputs. Okay, so this is AN, BN, X. Next state is AN plus 1, BN plus 1, and this is TA of n plus 1, TB of n plus 1. Okay, and so you start with 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1. Okay. Now based on this, you first populate these 2 columns for TA and TB. So TA of n plus 1 is just Bn and X. So it's just when both Bn and x is this thing. So therefore, this is very straightforward. This will be 0, 0, 0, 0, 0, 0, no, this will be 0, 0, 0, 1. Fourth entry will be 1, 0, 0, 0, 1. Likewise, for TB, it is just x. So you just reproduce this. Okay. And based on this, of course, let me 2, 3, 4, 5, 6, 7, and 8. Okay. So an plus 1. So now I am just going to look at flip-flop 1. Okay. I am going to only figure out what this next state is based on this characteristic table. So if TA is 0, okay, then it will just retain AN. It's just going to retain that state. So all I have to do is look at only these two for now. Okay, I don't have to look at the other two. So I'm looking at row 1. TA is 0. That means it will just retain whatever AN is. So you'll get 0 here. For the first 3 entries, you will just retain as it is. Okay, because TA is now 1 in the 4th entry, it will toggle whatever AN is, right? And therefore, you will get a 1 there. Then again, next 3 entries, you will just retain 1, 1, 1, 0, right? And therefore, the next state table will be like this for AN plus 1. BN plus 1 is going to be just X, right? Bn plus 1 is going to depend only on TB, right? And Bn, right? So TB is 0, means it's going to, on the first entry, TBN plus 1 is 0, and Bn I know is 0. So you will just retain this state. You will toggle this state. You will retain this state. You will toggle this state. You will retain this state, and you will toggle this state, retain this state, and you will toggle this state, right? So you will get B as 0, 1, 1, 0, Bn plus 1, 0, 1, 1, 0, 0, 1, 1, 0, right? And my output Y, by the way, that is just An and Bn, right? So this is 0, 0, 0, 0, 1, 1. Okay. Now, based on this, I can go ahead and just build my my state transition diagram. Okay, this is as usual the state table. Okay, and color coding, again very important. Y, An, Bn, An plus 1, Bn plus 1. Okay, so I have 4 states as usual. Zero, 0, 0, 1, 1, 0, 1, 1. Okay, and then the input is going to now come. If the input, if you are at 0, 0, which is, I'm analyzing row 1 now, input is X, you are going to remain at thing. So I'm looking at this thing here, right? So it will just remain, input is 0 and output will be a 0, right? So yeah, and likewise, if my in An and Bn in row 2 is 0, 0, but input is 1, then I go to state 1, state 0, 1, right? So the input is 1 and the output is a 0. Okay, the output is a 0 and yeah. Right. So now when I am at 0 1 state and I have an input of 0. Oh, I'm sorry, this is not correct because this is 0 1 1 0 1 1. Yeah. Okay. So this is exactly what it is. So I have, yeah, 0 1 correct. So I come to 0 1. So if I'm at 0 1, which is yeah, which I'm now analyzing row 3. If I'm at 0 1, input is 0, then I just remain at 0 1 and output happens to be 0, right? Then I come to 0 1 and the input happens to be 1, then I go to 1 0. So this will take me to 1 0, input is 1, output happens to be a 0, right? And then I have 1 0, I input is 1 0, input is 0 and output is going to be a 0, right? And the sixth row, if I am at 1 0 state and I have an input of 1, I go to 1 1, right? I go to 1 1 out here and this is input of 1 and my output is 0, still a 0, right? So finally I am at row 7 and row 8. If the state is 1 1 and the input is a 0, then I am at 1 1, right? So what do I do? I'm going to now remain at this state here. Okay, so 0, output is 0. No, output is a 1 now, right? And finally, if I am at 1 1 and the input is a 1, then I come back to 0 0 like this and the output is going to be a 1 again, right? So so what you see here is you know depending on the input x, so if x is actually just set to 1 always, right, this this guy is simply going to go from 0 0 to 0 1 1 0 1 1 and then back to 0 0, right? It's as simple as that. And based on that, you're going to just the output will go high or remain low as the case may be, right? So this is the analysis with a simple T flip-flop that I have shown you here. Okay, so going forward, we will look at the case of the inverse problem where we start with a state transition diagram, build a state table and then get it to a circuit level implementation that we want of a finite state machine. In this particular example, it just turns out that the output is not a function of the input. So if you go back and look at that circuit diagram also, the combinational block 2 does not take the input x as one of the inputs, right? It just depends on the current state, right? And therefore, this same state diagram can be drawn a little differently to indicate that as well. See, for example, here it's not clear that the output does not depend on the input x, right? It may so happen after Boolean simplification that is the case, but really this does not bring out that information. So therefore you could redraw this in a slightly different way like this. Okay. So here I will say 0 0. So if you look at this, state here, okay, irrespective of whether the input is 0 or 1, if the input is 0, you just stay at state 0 0 and then output 0. If the input is 1, you go to state 0 1 in this particular case, right? But the output is still a 0. So therefore you could indicate the output like this also. So in this state 0 0, it's only a function of this 0 0 value, okay? And likewise I could do 0 1, right? And the output is now going to be a 0 1 0, and the output is still going to be a 0, right? And then finally you come to 1 1, and the output is going to be a 1. And now I only worry about the input transitions here, where I have 0 1 0 1 0 1 0 and 1. So this makes it amply evident that the output in magenta is not a function of the red inputs at all. It's only a function of the blue state values, right? So this is an alternate representation of the same state diagram that is shown on the left here. Thank you.